Hey, this is Mr. Weisfeld. Time is flying by, ladies and gentlemen. It is Cinco de Mayo today. Yesterday was May the 4th be with you. And tomorrow, May 6th, will be 1 month before the last day of school, June 6th. So, let's take a moment and review where we are in Earth Physical Science in Semester 2. This stuff is going to be on the final, so let's talk about dates. Your final exam is going to be sometime in the week of May 19th through the 23rd. It will cover Inquiry A and B. That's writing questions, writing procedures. Inquiry C, writing conclusions. And it will cover PS2A, PS2B, and parts of PS2C. So that's structure of the atom, PS2A, periodic table, PS2B, and bonds. So how atoms come together and make molecules, and that will wrap it up. So your final projects are due May 30th. We have a little bit of time after that to play our games together or to share them with each other until the last day of school on June 6th. So here we go. Take your handout. You've got a few things to write down or take notes on what we're talking about here. So here we go. This, my friends, is the periodic table. One really important thing to remember, it's all about protons. So do not forget this one thing, which is it's about protons. Let me just circle it here. The number of protons determines which atom you're talking about. We start with one proton up here. That's also the atomic number. And we go all the way down to atomic number 111, 103, 71, depending on where you are at. Okay. Next thing to remember, this right here separates the metals from the non-metals, okay? So the things that are in green are called the metalloids. They share properties of metals and non-metals. But all this stuff over here, in blue, metals. Stuff in green, like we said. All this stuff over here and above, non-metals. Okay? Specific groups that we know about: halogens, noble gases, alkali metals, alkaline earth metals, transition metals. All good things to remember. The reactivity of the metals increases as you go this way and down. So reactivity. That was a major trend that we talked about. And reactivity increases as you go right and up here on the periodic table. You know that there's the symbol and that there's the atomic mass on each element in the periodic table. Okay, so that's the periodic table. Groups are columns, periods are rows, and you've used this, every day this semester. So don't panic. You know this stuff. All right. Next slide. If you wanted to see it in a table format or kind of in a summary, and this was what PS2B, some of our reassessment, was all about. Metals in blue, metalloids in green, non-metals in yellow. So metals have certain physical properties here, and non-metals have certain physical properties. Metalloids tend to share some of those. They can be in between. They sometimes might be shiny and sometimes they might be dull. Sometimes they might be conductive, sometimes they might not be conductive. We're generally going to ask you, if I give you a metal, you know that it's shiny, it's ductile, that means it can be pulled into a wire, it's malleable, and it's conductive of heat and electricity. If I give you a non-metal, you know that it's dull, it's brittle, so it breaks easily, it's not generally conductive, and a lot of times it's gases, turns out, which are all physical properties. Chemical properties. And let's talk about real briefly where we have some examples here. So some examples of metals: alkali metals, group 1. Alkaline earth metals, group 2. The transition metals, everything in between down there. The weak metals, the metals that are underneath the metalloids. Metals tend to rust. That's a reaction with oxygen over time. And metals tend to react with acids. Okay? So check those off if you know those. The metalloids, the ones that we talked about, the examples, this is it actually. This is not just examples. These are all the metalloids. Boron, silicon, arsenic, germanium, astatine, antimony, tellurium, all of those. They share some properties, even chemical properties. They sometimes might react with acids, sometimes they might not. All right, nonmetals. We have the noble gases, group 18. We have the halogens, and we have schnapps. Those are the elements that are important to life. So carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. They do not generally react with acids. That's probably just that's the main thing that we talked about when it comes to chemical properties. So keep this table in mind. Review this table. Review your physical properties. Review your chemical properties. You'll be set. All right. History of the atom. We spent some time. We had a video about this, and I'm gonna at the end of this video talk about some stuff that we've got on the Q drive, and of course there's some stuff on YouTube. So Democritus, Lavoisier, Dalton, J.J. Thomson, Rutherford, Bohr, Schrödinger, and Chadwick. You need to review some of this stuff here. So Democritus, starting off early on in ancient Greek, he said that atoms are indestructible, indivisible solid spheres. Seem reasonable? For a long time, that seemed very reasonable. It seemed very reasonable to you, these guys at least, and then things started changing. So Lavoisier talked about the law of conservation of mass. He studied combustion. Things react with oxygen. Then came Dalton. He's kind of considered the father or figure of atomic theory. So he's got the law of definite proportions. He says that elements are all the same. He says that they combine to make other things. So very key person right there. We spent some time talking about, so that was Dalton. We spent some time talking about Thomson. Cathode ray tube experiment. You should think of these words linked to Thomson. Plum pudding and electrons. All those come from Thomson. And we talked about Rutherford. The gold foil experiment. That's shooting these atoms at gold foil, and some bounce back incredibly. So he discovers the nucleus in that. And atoms are mostly empty space with a dense and positive center. Electrons are orbiting that. So all of these things you should pretty much link in your mind to Rutherford. I mean, if I say Rutherford to you, gold foil, nucleus, empty space, boom. Bohr, we talked about the hydrogen atom. Remember the ladder with levels of energy. Light comes from atoms being excited. That's all due to Niels Bohr. Electrons can jump. Schrödinger, electrons form a cloud around the nucleus. You can't really know exactly where they are at any given time exactly, and so that's electron cloud. This is also kind of the beginning of quantum mechanics, so modern physics, a modern understanding of the atom. And Chadwick, you should always link Chadwick's name to the neutron, so we're good there. All right, you need to be able to draw the atom. You need to be able to tell me where stuff is, and not just where it is, but that we have a nucleus. That's kind of a name for that center part. And you need to know what the charges are and what the masses are. So let's just double check that we've got this real quick. You can draw your atom most of the time. You can draw your atom here with electrons that are negatively charged whizzing about the outside. You've got a nucleus. Let me just circle it. Nucleus contains protons and neutrons in the center. Protons are positive. Neutrons no charge, okay? And electrons negative. Okay, so you've got to be able to draw what the atom looks like, and you got to be able to draw or tell me what the charges are. So protons are positive, neutrons no charge. and they're in the nucleus. Another thing that we need to talk about real quick, since the mass of the electron is mostly here in the nucleus, you need to know that a proton weighs about 1 atomic mass unit, a neutron weighs approximately 1 atomic mass unit, and okay, so they're almost equal in mass, protons and neutrons. That's why we count them up when we want to know the mass of an atom. And then you need to know that the electrons are very small mass-wise. Still some mass. So if you lose one, your mass of your whole atom goes down by a small amount, but not near as much as if you lost a proton or a neutron. Okay, so that's the atomic model as we understand it today. Hey, let's just do a quick chant. Protons, identity. Neutrons, variety. Electrons, reactivity. Okay? Protons, identity. Who you are as an atom. Your atomic number is how many protons you have. Neutrons, variety. Various flavors or isotopes of atoms have the same number of protons but different number of neutrons. That means they weigh differently. They have different masses, but they are still hydrogen, let's say, or boron, because they have the same number of protons. But neutrons make some variety, okay? Electrons are about reactivity. They're flying around the outside. You lose one, you become an ion. You gain one, you become an ion. Losing is positive, gaining is negative. But it's about reactivity. Why atoms do what they do is because of electrons. All right, so protons, identity. Neutrons, variety. Electrons, reactivity. Okay, try that a couple more times. All right, we talked a lot about this nuclide symbol, like a shorthand for how to write atoms. You've got the mass number, which is the number of protons plus the number of neutrons. You've got, let's just check it off here. Mass number goes in the upper left. It's equal to the number of protons plus the number of neutrons. It's not the atomic mass. Or not the atomic mass. It's the mass number. Atomic number bottom left. Sodium is always 11. It's the number of protons. Atomic number. The charge. If an atom loses an electron or gains an electron above neutral, so remember there's neutral, which is no charge. That means your number of protons equals your number of electrons. That means sometimes you won't see anything up here. It'll be like a 0. But if you have a charge, if you're an ion, you've gained an electron or lost an electron, then you have a charge up here. And it could be +2 or 2+, or it could be 3-, right? All of that's going to be written up here in the charge. The symbol, of course, you look it up on the periodic table. It's the number of protons. That tells you what you have. The atomic mass, that's something you've got to look up on the table. It's a calculation of a bunch of atoms, different neutrons. It's about how many in nature there are of a certain type of atom with a certain number of neutrons. It's a weighted average. So, but you look that up on the periodic table. And when you want to know the number of neutrons from this symbol here, you subtract the mass number minus the number of protons. So take this minus this. Here, I have 12 neutrons, right? Because that equals 23 minus 11. And I think for sodium, is that the most common? I'll get back to you on that. But you can look it up. Somebody stand up in the room right now and tell me if that's common or not. Look it up. All right, that's the mass number. The number of electrons is the number of, it's the atomic number, which is the number of protons minus the charge. So 11 minus 1 means there's 10 electrons. 11 minus 1, or 11 minus 2, or 11 minus, now watch this, minus 3 means you have way more electrons than protons. That can be 14, right? All right, so that is the nuclide symbol. That's a fancy word for what we call this kind of numbers, letters, etc., talking about an atom. So study this, memorize this. If you got this, you're good for the test. All right, hey, one more thing. And we've got this week to kind of solidify this, make sure we understand this. There's different types of bonds between atoms, if they have lost an electron or if they're sharing electrons. Let's watch this guy, Tyler DeWitt, on this real quick. He'll explain it to us, and then we'll review it, and then we'll be good. So check this out.
In this video, we're going to look at compounds that are ionic versus compounds that are molecular, also known as covalent. We'll learn how you can tell them apart based on their formulas, and then we'll look at some important differences between them. So, how can you tell whether something is ionic or molecular? Well, it depends on the elements that make them up. So, ionic compounds are made of metals and nonmetals, whereas molecular, also known as covalent compounds, are made of only nonmetals. Let's do a couple practice problems to work on this. You will need a periodic table to do this. Here's the one that I'm using. I've left out a lot of the elements because they're not important, but what is important is this big, thick staircase that divides the periodic table into two parts. On this side of the staircase are the metals, and on this side of the staircase are the nonmetals. Okay, so here are a couple examples. The first one, sulfur dioxide. So what are the elements it's made of? It's made of sulfur and oxygen. Both of these are nonmetals, which means that sulfur dioxide, SO2, is a molecular compound. Sodium chloride is made of sodium, a metal, and chlorine, or chloride, which is a nonmetal. So sodium chloride is an ionic compound. All right, now, H2O is made of hydrogen and oxygen. Now, you might think that hydrogen is a metal because it's on this side of the periodic table. It's fine, it's understandable if you do that. But hydrogen is an exception. Even though it's on this side of the periodic table, it's actually a nonmetal. It's the only exception. So hydrogen and oxygen are actually both nonmetals, which means that H2O, water, is a molecular or covalent compound. Okay, copper 2 fluoride. Copper is here, fluorine or fluoride is here, metal, nonmetal, so this thing is ionic. Okay, let's look at a few trickier examples. So far, we've only looked at compounds that have two elements in them, but there are a lot of compounds out there that have more than two elements in them, okay? So propanol, for example, is made of carbon, hydrogen, and oxygen. All three of these are nonmetals, though, so this is still a molecular or covalent compound, even though it has a bunch of nonmetals in it, okay? Don't be confused by that. Here's another example. Lithium nitrate has lithium, which is a metal, but then it also has nitrogen and oxygen, which are both nonmetals. So it's still got the metal, nonmetal thing going on, so it's an ionic compound, even though it has two nonmetals. And the same thing is true of sodium sulfate. It's got sodium, a metal, and two nonmetals, sulfur and oxygen, but metal, nonmetal means it's ionic. Now, lithium nitrate and sodium sulfate are actually special kinds of ionic compounds because they have two different nonmetals in them. They are what are called polyatomic ionic compounds. If you want to learn more about these, I've got videos on that. So now we can look at a chemical formula and we can sort them and we can decide whether something is ionic or whether it's molecular or covalent. So what? Who cares? Well, there are some very important differences between ionic compounds and molecular compounds. Let's take a look at some of those right now. So one really important difference is how the atoms in these compounds are held together. In molecular or covalent compounds, the atoms that make them up are held together because they're sharing electrons. Here's what I mean. Water, H2O, is a very common molecular compound. It's made of one oxygen and two hydrogens, and these lines between the atoms show that they're connected, and they mean that they're connected because they're sharing electrons. Here's how I like to think about this. It's like oxygen and hydrogen both have these little hands, and the hands are joined together. It's like they're holding hands, and they're holding hands because they both are trying to hold on to a pair of electrons, which I've drawn here in red. So we've got oxygen and hydrogen connected together because they're holding on and sharing these electrons here. That's what makes the atoms connect and stick together in a molecular or covalent compound. Okay? Now, on the other hand, in ionic compounds, the atoms aren't being so nice to each other. Okay? They're not sharing. The atoms stick together in an ionic compound because one atom steals another atom's electrons. So electrons get stolen, and then opposite charges attract. Let me show you what I mean. So sodium chloride, or NaCl, is a very common ionic compound. It's made of sodium and chlorine, and here they are just hanging out. Now for these two guys to stick together, here is what happens. The first thing that happens is chlorine reaches its greedy hand over and grabs an electron from sodium, okay, and it pulls it back. So now chlorine has an extra electron and sodium has lost one of its electrons. This causes chlorine to now get a negative charge because it has a new electron, and sodium, because it's had one of its electrons stolen, now it has a positive charge. So now we have a positively charged ion here and another negatively charged ion here. What do opposite charged things like to do? They like to come together. They stick together. They're attracted to each other just like magnets. So now we have a positively charged thing and a negatively charged thing. These arrows show how they're going to come together. And we end up with the two atoms stuck together because they're oppositely charged. And that's what holds ionic compounds together. So covalent or molecular compounds, the atoms are stuck together because they're sharing electrons with each other. Ionic compounds, the atoms are stuck together because one has stolen the other's electrons, it's given them opposite charges, and then those opposite charges have, let me try that again, and then those opposite charges, there we go, have attracted just like magnets. So this is one way that ionic and molecular compounds differ. Here is one more. So another big difference is how these compounds would actually look if we could see the atoms that make them up. So molecular or covalent compounds are made of molecules, which is a fancy word for a bunch of atoms that are stuck together in a clump. Here's what I mean. So sugar is a very common type of covalent compound, and it is made of molecules where I have these atoms here stuck together in a clump. 2 carbons, 4 hydrogens, and 2 oxygens. So a grain of sugar would look like this. It would look like a number of different sugar molecules that have all kind of come together and formed a clump here. Okay, but the big deal here is that these molecules are individual clumps of atoms that then come together to make stuff. On the other hand, ionic compounds, they're not made of clumps of atoms like molecules. They're made of what we call lattice structures. And here's what lattice structures are. The example I'm going to give you is salt, which is sodium chloride, table salt. And the lattice structures of sodium chloride look like this. Look how different this is from the molecules that make up sugar. You just have the sodium and the chloride atoms stuck together in this sort of very organized box-like shape. This is what a lattice structure is. There aren't individual clumps of sodium chloride the way there are individual clumps of sugar. Instead, all the atoms are stuck together in this very regular shape. Now, one big important difference between covalent and molecular stuff and ionics is what happens when they dissolve in water. These guys just come apart into molecules, whereas the individual atoms come apart when an ionic compound dissolves in water. But we're getting a little ahead of ourselves here. If you're interested in other differences between these, check out videos that I have on the physical properties as well as what happens when you dissolve ionic and molecular compounds.
Right. So thanks. That was Tyler DeWitt. A lot of this stuff is up on YouTube. So here is a summary of what we just talked about. There's types of bonds, 2 different ones, main ones that we're talking about. There's covalent and there's molecular. Covalent, molecular, and ionic. So the 2 types of bonds are 1, this one, 2, this one, ionic. They can be described in the following ways. Which elements generally come together, or how are these made up? So covalent molecular is usually between nonmetals to nonmetals. It's mostly that stuff in the upper right of the periodic table. On the other hand, ionic bonds are usually between metals and nonmetals, or metals or a group of nonmetals. But the trick is you've got a metal in these. So if you've got a metal, you should start suspecting some ionic bonds going on. Then, when it comes to electrons, we got to talk about what happens to those electrons. So in this case, we're talking about valence electrons. These are outer shell electrons. We'll review that again, but electrons are shared, okay, in covalent molecular bonds. In ionic bonds, electrons are stolen from the metal to the nonmetal. Remember, if you steal one, you make a positive ion, and if you gain one, you make a negative ion, and then those attract. So these attract, whereas these just kind of come together because they're sharing electrons. Then how do they look? If you could look at them under a very powerful microscope, you see basically clumps of atoms, or in these you see very organized lattice structures. And when you put them in water, these break up into the separate ions. So sodium chloride will break up into Na+, Cl-, and H2O, of course, is water itself. It doesn't break up, but it's basically clumps of atoms. Okay, so those are the types of bonds. Let me just review a couple things here at the end of this video. All right, so a couple things to note. On the Q drive, you have a lot of these videos. Q drive, Earth Physical Science. Weisenfeld. And then I think I've put all the videos under archive. So Earth Physical Science Weisenfeld Archive. Look for things about PS2A. If you need to know about the structure of the atom, look for names that start with PS2B. If you need to know about the periodic table, look for things that begin PS2C. If you need to know about bonds. And now look for things that start with INQA. INQA if you need to know about inquiry A, writing questions, inquiry B if you need to know about procedures, or inquiry C if you need to know about writing conclusions. All of those things are going to be covered on the final exam. This is what you can study. You can also, don't forget, why you know reassess. You can still reassess any of the quizzes that we've had up till now to improve your grade, and so that your final grade, a combination of your grades on quizzes and then your grade from the final exam on a standard, will determine your final grade. Then your project can also help out your grade. So, all right, that's it for today. Thanks for listening. This is Mr. Weisenfeld.